All right, welcome everyone. This is going to be a relatively brief lecture today. We're just going to be introducing blood pressure and having kind of a general overview of it. And after this lecture, there will only be one more left in this unit. So let's go ahead and get rolling with our not really attendance questions. If afterload were to increase, what would be the effect on cardiac output? Cold temperature decreases heart rate. What would be the effect on cardiac output? Immediately prior to the T wave, what would be the pressure in the aorta? And what is the role of a basophil? So try to answer these on your own, and let's see what the correct answers should be. If afterload were to increase, well, first let's think about what afterload is. Afterload, remember, was the pressure in the aorta immediately prior to ejection of blood from the ventricle. Or we said that it was the pressure that must be overcome before blood can be ejected from the ventricle. So if afterload were to increase, that makes it harder for blood to leave the ventricle, which means cardiac output would go down. If afterload goes up, cardiac output goes down. Cold temperature decreases heart rate. What would be the effect on cardiac output? Well, stroke volume and heart rate are the two things that determine cardiac output. So, if if heart rate were to go down because of cold temperature, then cardiac output would go down. Immediately prior to the T wave, what would be the pressure in the aorta? Okay, so first we have to think about what's going on immediately prior to the T wave. So that flat spot in front of the T wave, what's happening there? That's when the ventricle is in systole. That's when the ventricle is contracting. So the ventricle is pressing blood into the aorta on the left side. And as the aorta is filling with blood, pressure is rising to its highest point. And we said that pressure in the aorta during ventricular systole, which is what is immediately prior to the T wave, is 120 mmHg. And finally, what is the role of a basophil? Basophils were white blood cells, leukocytes, and among other things, what they're really most known for is release of histamine and a few other related chemicals. So histamine is released from basophils. Okay, so we've talked now about how the heart works. We've talked about all of the electrical stuff, all the mechanical stuff. We've talked about how blood actually is ejected from the heart. So we've covered the heart pretty well. Now we're going to jump ahead to chapter 20, and we're going to wrap everything up in these next two lectures. Everything is going to be about blood pressure, and we've kind of briefly touched on blood pressure, but without actually really getting into it. So let's now look at what blood pressure is, and then later, over the next two lectures, we're going to start talking about factors that affect blood pressure and how your body maintains blood pressure. So blood pressure typically is written in something like the form of 120 over, it used to be 120 over 80 was considered normal. After re-examination, it's 120 over 75 is now what's considered normal. And those are both in mmHg because they're pressures. And remember, all pressures this semester are going to have the same units, millimeters of mercury. Now, this top number is called the systolic arterial blood pressure. The systolic arterial blood pressure. And this is when the heart is at its most contracted and the blood has been pushed out of the ventricle into the aorta. This is the pressure in the aorta during that time. and it's actually going to be determined by the force of contraction of the ventricle. The force of contraction of the ventricle is going to push blood either more forcefully or less forcefully into the aorta. So this number on top, the systolic arterial blood pressure, is determined by that force of contraction. The bottom number, 75 mmHg, is called the diastolic arterial blood pressure. This is the pressure in the aorta when the ventricle is in diastole. When the ventricle is in diastole, it's not pushing any blood into the aorta. So the aorta is not receiving any blood. Pressure drops, but it doesn't drop to zero. It still has blood inside of it. And remember, blood vessels, they have a lot of elasticity to them. That tunica media, there's a lot of elasticity. So it's kind of like when you put a rubber band around your forearm. Well, the rubber band squeezes against your forearm and you feel pressure. Well, the arteries, such as the aorta, squeeze on the blood that's inside of them. So there is still pressure there. The diastolic arterial blood pressure is determined by peripheral resistance of the aorta. So we're going to talk a little bit about peripheral resistance later. We've introduced it back when we first introduced blood vessels, but to refresh you, remember, peripheral resistance is the opposing force to blood moving through a vessel. When peripheral resistance is up, it's harder for blood to move through that vessel. When peripheral resistance is down, it's easier for blood to move through that vessel. So 120 over 75 is just the systolic arterial blood pressure over the diastolic arterial blood pressure. And if we take the difference in the two, that's called pulse pressure. Pulse pressure is just systolic minus diastolic. And the normal blood pressure, the average healthy adult male, the blood pressure is 120 over 75, so the pulse pressure is 45 mmHg. Pulse pressure, 45 mmHg. 120 minus 75. Next, mean arterial blood pressure, or MAP. Mean arterial blood pressure is a way of saying, yes, with every beat of the heart, blood pressure rises to 120, drops to 75, rises to 120, drops to 75, and it just keeps going on and on and on. So blood pressure is constantly changing. MAP is kind of the average of that blood pressure. MAP is actually the force that propels blood through your blood vessels. Rather than saying 120 over 80, this is a way of giving a single number to those pressures. And we can find MAP two different ways. One is by taking diastolic pressure and adding 1/3 of pulse pressure. So pulse pressure, remember, was 45 mmHg. If we take 1/3 of that and add it to diastolic pressure, then what we get is 90. So let's see how we did that real quick, just in case. I know I don't like math, so I know a lot of students also don't like math. Well, pulse pressure, remember, was what? It was 45. But if we take 1/3 of that, then that is 15. Add diastolic pressure, which is 75. So 75 plus 15 gives us 90 mmHg. So MAP is 90 mmHg. But there is another way to figure out MAP. There's another equation, and that is cardiac output times peripheral resistance. Cardiac output times peripheral resistance. Now, if you have been kind of looking ahead and going over things also that we talked about previously, this may look familiar. It may look familiar. Hold on just a moment. There's that page, which is the last page of our outline. Does anything look familiar here? Well, across the top we see blood pressure is equal to cardiac output times peripheral resistance. But over here, we said MAP was equal to cardiac output times peripheral resistance. So what does that mean? It means MAP and blood pressure are the same thing. It's just typically when we talk about blood pressure, we think of two numbers, systolic over diastolic. When we talk about MAP, it's a single number, 90 mmHg. But when we're talking about pressure and we're talking about the force that propels the blood, it's not the rising and the dropping, it's the constant. And that's kind of what we can think of when we think about MAP. MAP is almost the average. It's not the average. We can see up here how it was determined. But we can think of it almost like an average pressure that's constant in our vessels. Now, blood pressure, and from now on we can think of blood pressure and MAP interchangeably. Blood pressure drops as distance from the aorta increases. So in the aorta, that's where blood pressure is highest. As we move further away from the aorta, that pressure starts to drop. So we have a graph here that it shows us a couple of things. First, down here's the vessels as we're moving further and further and further away. So the very first thing here is the aorta. And we can see 120 over 80, 120 over 75, thereabouts. And we can see that there's quite a big difference between the systolic pressure and the diastolic pressure. And as we get further and further and further away, that pressure is dropping, and also the difference between systolic and diastolic gets smaller. Once we get to the capillaries, there is no difference between systolic and diastolic. Once we're in the capillaries, we only have a single pressure. And from that point on, it's just a pressure, and that pressure is dropping until we get to the vena cava, when, like I said, it's practically immeasurable. So, blood pressure. Blood pressure is equal to cardiac output times peripheral resistance. That chart, that's the last page of your handout, I say know it to the point that you see it with your eyes closed. I am not going to ask you to reproduce that chart. But if you know that chart and the layout, then it's really, really easy to understand how all of those factors influence blood pressure. Well, we've talked about stroke volume, and we've talked about heart rate, and we're going to come back and talk more about them in our next lecture. But there's still one more factor that affects blood pressure that we have not talked about, and that's that peripheral resistance. So now we're going to start talking about the stuff on the right-hand side of that chart. Peripheral resistance. And there are different factors that affect peripheral resistance. There are 3 of them. First is blood viscosity. Remember viscosity? Viscosity was resistance to flow. Remember when we talked about resistance to flow way back on one of the very first lectures this semester? We talked about resistance to flow, viscosity. One way that we can affect viscosity is polycythemia. Polycythemia. Remember, polycythemia is excess erythrocytes. And if we have excess erythrocytes, our blood is going to get thicker. That's why we said that blood doping was such a bad idea. Polycythemia causes your blood to get thicker, which makes it harder for our heart to move that blood. Total blood vessel length. The longer your vessels, the harder it is for blood to move through them. And this is one of the reasons why obesity is so bad on the heart. Because if you are obese, you have more tissue. And in order to supply that tissue with nutrients and oxygen, we need more blood vessels. Our blood vessels have to be longer to supply that new tissue. Obesity increases blood vessel length, and an increase in blood vessel length increases peripheral resistance. Vasodiameter. We briefly mentioned this when we first started chapter 20 a few lectures ago. Vasodiameter is just the diameter of a vessel. So here's a large vasodiameter, a smaller vasodiameter, and a really small vasodiameter. Now, if we were to take this middle and say, expand it, vasodilate it. If we dilate a vessel, it gets bigger. It now has a larger vasodiameter. Or if we take this vessel and we constrict it, we make it smaller. It has a smaller vasodiameter. So vasoconstriction makes the vessel smaller. Vasodilation makes the vessel larger. So we can change vasodiameter. Well, when we constrict, when we have a smaller vasodiameter, peripheral resistance goes up. When we dilate and we have a larger vasodiameter, peripheral resistance goes down. Let's think of why this is. Let's say you and a group of 10 friends are walking down a hallway, and suddenly that hallway gets about 1/4 as wide. Is it easier or harder for all of you to move through together? It's harder. The peripheral resistance increased. But if the hallway gets much larger, much wider, well, now it's easier for you and your friends to get through. The peripheral resistance decreased. The bigger the space, the easier it is for something to move through it. The smaller the space, the harder it is for something to move through it. Vasodiameter. Well, we can regulate vasodiameter. There's actually several naturally occurring chemicals in our body that do just that. For example, something called ADH, the antidiuretic hormone. I don't believe we've mentioned this just yet this semester, but we are going to talk about this now the rest of the semester. ADH, the antidiuretic hormone, is a hormone that plays a role in practically every chapter this semester. Antidiuretic hormone is also called vasopressin. Vasopressin, sometimes called arginine vasopressin. But ADH is a vasoconstrictor. So, if it's a vasoconstrictor, that means it takes a blood vessel that looks like this and then causes it to look like this. That's not the main role of ADH. We'll see the main role of ADH later in another lecture. But in really high amounts, when ADH is very high in the body, it is a vasoconstrictor. And ADH, when it causes vasoconstriction, it increases peripheral resistance. ADH causes vasoconstriction, which increases peripheral resistance. Ang2, or angiotensin 2. This is another hormone that is also a vasoconstrictor. As a matter of fact, angiotensin 2, Ang2, is the most potent vasoconstrictor in our body. So when Ang2 levels are up, we get vasoconstriction. And when we get vasoconstriction, peripheral resistance increases. ANP, the atrial natriuretic peptide. ANP, the atrial natriuretic peptide. ANP is a vasodilator. It takes a vessel like this and causes it to dilate, opens it up. So when ANP is up, we get vasodilation and peripheral resistance goes down. Finally, inflammatory chemicals, such as histamine. That's why I asked about basophils earlier. Inflammatory chemicals, such as histamine, cause vasodilation. Vasodilation leads to a drop in peripheral resistance. This is one of the reasons why people who have something like anaphylaxis often pass out. If they have severe allergic reactions, they will get severe vasodilation, and now their peripheral resistance is so low that causes a drop in blood pressure, and they will faint. Also, increase or decrease in SNS. What about PNS? Well, normally when SNS does one thing, PNS does the opposite. If SNS causes increased heart rate, PNS caused decreased heart rate. That's how it is most places in the body. But the parasympathetic nervous system does not have any control over vasodiameter. Only the SNS does. When SNS is up, we get vasoconstriction. When SNS is down, we get vasodilation. Nothing to do with parasympathetic nervous system here at all. This is all sympathetic. Sympathetic causes vasoconstriction, and peripheral resistance increases. Deactivating the SNS causes vasodilation, and we get a drop in peripheral resistance. All right, so the rest of this chapter is going to be covered in our next lecture. That will be the final lecture for Unit 1. And it's going to look at how does our body maintain blood pressure and regulate blood pressure.